Okay, so today we're talking about Chapter 1, Section 1, the real number line and absolute value. Alright, so numbers and number concepts form the foundation for the study of algebra. In this chapter you will learn about positive and negative numbers and how to operate with these numbers. The following list indicates ways that positive and negative numbers occur frequently in our daily lives. Right? So temperatures are recorded as negative numbers when they're below 0, 0 when they're 0, and then positive when they're above 0. The stock market will show a loss if we're at negative, no change if we're at 0, or a gain if we're positive. The altitude can be measured below sea level if we are negative is below sea level, 0 if we're at sea level, and positive if we're above sea level. And then business will report losses if their income is negative, break even if they're 0, or profits if they are positive. Right? Number lines. The study of algebra requires that we know a variety of types of numbers and their names. The set of numbers, denoted by this funny looking N right here, is called the natural numbers or counting numbers. The three dots at the end indicate that the pattern continues on without end. Putting 0 with the set of natural numbers gives a set of whole numbers, which we see here. So natural numbers just go 1 to infinity. Whole numbers are the natural numbers just with the number 0 added on with it. Thus, mathematicians make the distinction that 0 is a whole number, but not a natural number. So to help in understanding different types of numbers and their relationships relationships to each other, we begin with a picture called a number line. For example, choose some point on the horizontal line and label it with the number 0. So in this particular figure, we're just going to draw a horizontal line. We're just going to make a vertical line and just going to call it 0. Right. So now we choose another point on the line to the right of 0 and label it with the number 1. We see that here. This point is arbitrary. Once it is chosen, a scale is determined for the remainder of the line. So pretty much the distance between this 0 and this 1 is going to be pretty much the same distance we're going to go to 2, 3, 4, as we'll see down here in figure 3. Alright, so we now have a number line. Points corresponding to all the whole numbers are determined. The point corresponding to 0 is the same distance from 1 as 1 is from 0. The point 3 is the same distance from 2, and so on, as we mentioned earlier. So the graph of a number is the point that corresponds to the number, and the number is called the coordinate of the point. We will follow the convention of using the terms number and point interchangeably. For example, one point might be 7, and another point is going to be called 2. The graph of 7 is shown by the large red dot in figure 4. Okay, so we are denoting that we're at 7 here. So the graph of the set A, right, again, A being a set, is 2, 4, and 6. Okay, so that's what we call set A. On a horizontal number line, the point 1 unit to the left of 0 is the opposite of 1. It is called negative 1 and is symbolized by a negative 1. Similarly, the point 2 units to the left of 0 is the opposite of 2, which we call negative 2, and so on and so forth. We have a 0 here, and then going 1 to the left is negative 1, then negative 2, negative 3, negative 4, which again, as mentioned earlier, is the opposite of the right side here. So the third definition here is what we call integers. Okay, so real quickly, whole numbers, I'm sorry, not whole numbers, let's go back to natural numbers. All right, natural numbers are 1 to infinity. Okay, so they're called natural numbers because they're numbers that you see naturally. You know, you see 6 trees, you see 14 chickens, right? You don't see 0 trees, right? Or you don't see negative 14 chickens. You don't see them. They don't occur naturally. Okay, so that's a natural number. Numbers that you can see naturally. Whole numbers are just, again, natural numbers with 0. Now, integers are all the whole numbers. The negative whole numbers, the positive whole numbers, and 0. Let's see. Okay, yeah. Negative whole numbers, positive whole numbers, and then 0. Right. The natural numbers are also called positive integers. Their opposites are called negative integers. 0 is its own opposite and is neither positive nor negative. right? So we see here that 0 is indeed equal to negative 0 because, well, it's neither positive nor negative. Note that the opposite of a positive integer is a negative integer, and the opposite of a negative integer is a positive integer. And we see that here. All right, so let's jump into some examples. We can probably fit a couple of these on this page. Their solutions seem pretty simple. We're actually going to go ahead and pull up this particular solution. We'll just do these two for right now. Okay. Alrighty, so I should probably snip the actual numbers that are being wanted right here to find the opposite integer. Alrighty, so example 1 reads, find the opposite of each integer. Alrighty, so what is the opposite of a positive 7? Well, the opposite of a positive 7, well, that should be the opposite of it. So that's just going to be a negative 7, right? And then b, what is the opposite of a negative 4? Well, all we're going to do is simply change the sign of it, right? So we're just going to change it to a positive 4. That's it. That's the opposite. It's just if it's positive, change to a negative. If it's negative, change it to a positive. Now over here, I snipped the number line just because I don't feel like drawing a number line here because these are nice and pretty. So this reads graph each set of integers. Okay, so what happens here is we're going to draw a number line. Actually, you know what? Let's just go ahead and kind of give a brief abbreviated drawing here. Right. So again, as mentioned earlier, what we do is we're just going to start here at 0, right? And then again, it's just an arbitrary spot, but I like to put 0 in the middle if I know how far out I'm going left or right. And then we're going to go right 1, 2, 3, 4, and then left 1, 2, 3, 4. We're going to try and stay consistent with the distance, right? Obviously, you know, these aren't exactly the same distance apart from one another, but that's just the way it is. That's also why I snipped the entire solution to example 2, because it's a lot prettier that way. But anyway, so problem A says graph each set of integers, -3, -1, 1, and 3. So in order to graph those integers, right, so if 0 is here, then this is -1, -2, and -3 would be right here. Okay, so I'm going to graph -3, and we said -1 is right here. Then we said 1 would be right here if we corresponded on the other side. So 1 and then 2, 3. So we're going to make our last point right here. Okay, and it's pretty similar to the solution there, but obviously, you know what? My drawing isn't too bad. Let's actually denote some points here. So 2, 4, and then 2, 4. Okay, I could write a 3 there. Excuse me. I could write a 3, but it just gets kind of messy there if I try to slip in a -3 and a +3, and along with the 1 as well. Oh, I didn't even go over the second one. Alrighty, so graph each set of integers. So we have a -4, -2, -1, 0, and 2. So as you can see on the graph, we do indeed plot the points at -4, -2, -1, 0, and 2. Alright, so I'm pretty sure. Okay, so numbers that can be written as fractions. Alright, starting at the top. Numbers that can be written as fractions and whole numerators and denominators are integers that have the technical name rational number. Okay, so rational number, if you recall, the term there, or sorry, not the term, but the operative word is ratio, right? Ratio being a fraction. So when we say rational numbers, we're talking about fractions. Okay. So variables are needed to be able to state rules and definitions in general form. The definition is restated here for easy reference and for emphasis, right? So a variable is a symbol, generally a letter of the alphabet, that is used to represent an unknown number or any one of the several numbers. All right, so variables, real quickly, I've heard, and it's I guess it's it's a funny joke, I guess, that people might say, yeah, I was good at math until they started putting letters in my math, right? And again, it's a funny joke, but the thing is, we use the letters because it's either letters or question marks, right? Because if we say x, oh, let's see, oh, we're on white. Hang on a second. Let's change to red. If we say, and I'm gonna erase the imaginary white. I don't know where I put it, but it's there somewhere. So if we said x plus 7 is equal to 11, right? That's an algebra problem that you're used to seeing. Well, if we didn't use letters, if we didn't use the letter there, then we would say question mark, right? Question mark plus 7 is equal to 11. And it just doesn't flow real well if we put a question mark. And that's really all a variable is just an unknown. Right? So the variables a and b are used to represent integers in the following definition of a rational number. So we have our definition of a rational number here. So rational numbers. A rational number is a number that can be written in the form of a over b, where a and b are integers, and b is not equal to 0. Okay, so a and b are integers, right? And we defined integers earlier. They were basically just the whole numbers. Every single whole number you can think of, both positive and negative, right? And we know that b cannot be equal to 0, okay, because we cannot have a 0 in the denominator. Or an alternative definition is a rational number is a number that can be written in decimal form as a terminating decimal or as an infinite repeating decimal, right? And I'm pretty sure we'll touch on that here in a moment. But just to kind of give you an idea, so like 1/4, okay? So 1/4. If I want to put this, all right, 1/4 is obviously, it's an integer over an integer, right? And of course, the 4 is not equal to 0, so we're good there. That is indeed a rational number. But we can also write that in decimal form, and it does have a terminating decimal, right? If I wrote this in decimal form, it would be 0.25, and it stops there, right? And the repeating part, right, the repeating decimal part would be something like 1/3. So if I had 1/3, that's the same thing as saying 0.333 all the way to infinity, right? So we can repeat it. So that's what a rational number is. It's a number that can be written as a ratio, or with a terminating decimal or repeating decimal. So numbers that cannot be written as fractions with integer numerators and denominators are called irrational numbers. Right? So rational numbers are numbers that can be written with in fraction form. Numbers that cannot be written in fraction form are called irrational. This includes numbers like the square root of 2, the square root of 3, pi, and the cube root of 5. These numbers can be written as an infinite, non-repeating decimal numbers. So all rational numbers and irrational numbers are classified as real numbers and can be written in some decimal form. They can also be represented on the number line. The number line is also called a real number line. Okay, so let's go back and discuss all the numbers we've talked about just now. Not numbers, but all the classifications we've talked about. Okay, so we started with natural numbers. Okay, and if you recall, it was kind of like a bold, funny-looking N. So the way I write natural numbers is I kind of just do two vertical lines, two better vertical lines, something like this. Okay, and we know that natural numbers, they were the set 1, 2, 3, dot, 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 all the way to infinity, right? That's the natural numbers. We got the whole numbers, which were the natural numbers, just with the number 0 included. 1, 2, dot, 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 all the way to infinity. Okay. And then next we had the integers, which were the negative numbers. -3, -2. Oh, hang on. We're going to go negative infinity, negative 3. Let's just do negative 2. Negative 2, negative 1, 0, 1, 2, dot, 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 infinity. Okay. And then we got the rational numbers, which we denote as Q. Okay. And these are just fractions, right? These are fractions. And so as we're moving up, notice how the whole numbers contain the natural numbers. Notice how integers contain the whole numbers and the natural numbers. All right. Now fractions, as you'd imagine, also contain the integers, the whole numbers, and natural numbers. How is that? Well, if you recall, let's just take the number 3, for example, right? The number 3 can be written as a fraction, 3 over 1. Okay, so that's how we can excuse me. That's how we can say that a number. I'm sorry. That's how we can say fractions are indeed, larger than your integers because they include the integers, right? And then we have your real numbers. All right. So, well, yeah. And then we have your real numbers. All right. The real numbers are every number, just every number, every possible number. Okay. So this is kind of the order that we're looking at, right? The reals are larger than the rationals. The rationals are larger than the integers. The integers are a bit larger than the whole numbers, and the whole numbers are larger than the natural numbers. Okay, rational numbers. I'm sorry, not rational. Real numbers, as we mentioned, include every single number you could possibly think of, including these numbers up here. That have infinite non-repeating decimal numbers. All right, so examples of rational numbers. These are examples of rational numbers. These are ratios that have terminating decimals or repeating decimals. These are examples of irrational numbers, numbers that go on forever. Okay, they do not end. And of course, this is pretty much the same thing I just showed you. Natural numbers, whole numbers, integers, rational numbers, and then real numbers. All right, so let's snip a couple examples here. And we're just going to snip these two together. All right, starting with example 3, it reads, list the numbers in the set that are A whole numbers. Okay, so whole numbers are going to be, well, it looks like it's just going to be a -5. It's going to be, ooh, I'm sorry, I messed up. It's whole numbers, Sherman. It's going to be a 0, and it's going to be a 17. Okay, so these are examples of whole numbers. Okay, so B, integers. All right, so integers now will include -5. So -5, 0, and 17. C, rational numbers. Okay, so rational numbers again are simply ratios, right? Fractions. So we're going to include in this time we're going to include the number 3/4. So we're going to have a -5, a -3/4, 0, and then 17, right? Because if you recall, -5 is indeed a fraction because it's -5 over 1. All right, now obviously this is a fraction, and then 17 is a fraction because it's 17 over 1. And 0 is also a fraction because it's 0 over 1. Right? So these are all examples of rational numbers. And then real numbers, well, they are all real. Okay, every one of them are real, or in the entire set S. The set is all real numbers. Okay, because I mean real numbers are, well, every single number you could possibly think of. So let's go look over here to the right, and we have, it reads, graph the set of real numbers. Okay, so we're going to graph the set of real numbers. Well, real numbers, again, are just every single number. So we're just going to graph every single one of these numbers to the number line. Right? Now this reads, graph all natural numbers less than or equal to 3. Okay, so natural numbers, if you recall, are numbers 1 to infinity, and it says all natural numbers are less than or equal to 3. So we graph 3, 2, and 1, and then we're done. Right? Those are all the natural numbers that can be graphed in that particular example. Right. So next up we have inequality symbols. Let's go ahead and snip this. Okay, so can we squeeze this down here? Kind of, not, maybe, so. It's close. It's close. All right, it's so close, I don't want to do that. All right, so just reading left to right here. So on a horizontal number line, smaller numbers are always to the left of the larger numbers. Two symbols used to indicate order are this caret to the left and this caret to the right. So this is read as the less than, this is read as a greater than. So using the real number line in figure 10, you can see the following relationships. So this is figure 10, right? We can see the relationships. We can see that negative 7 is less than negative 4, right? And we can see that 3 is greater than negative 2, because as we go to the right, we're going to the larger numbers. As we go left, we're going to the smaller numbers. And two other symbols that are commonly used are the less than or equal to and the greater than or equal to's, right? So basically what that means is, well, it says, for example, 5 is greater than or equal to negative 10 is true since 5 is greater than negative 10. Also, 5 is greater than or equal to 5 is true since 5 indeed does equal 5. And of course, we saw that, an example of that on the previous page here. This said graph all natural numbers that are less than or equal to 3. So 3 is equal to 3, so that's good. And we graphed all the values that are less than or equal to 3. All right, so symbols of equality and inequality. Reading from left to right, these are well, we didn't touch on the equal sign, but I mean that's we've seen the equal sign before, right? So the equal sign means obviously is equal to, and then the equal sign with a line through it means is not equal to. Okay, so those are two more things, but I'm pretty sure those are two things that you have seen before. So let's look at A. So determine whether each statement is true or false. All right, so 7 is less than 15. That is indeed a true statement. Okay. 3 is greater than negative 1. That also seems to be a true statement. See, now we're getting into fractions and with negative numbers here, okay? So what this is saying, it's saying that negative 1/2 is going to be less than negative 1/4. Okay, so if we were to look at a number line here, just bust out a number line. Right, if we have an arbitrary 0 here, okay, we're going to have a negative 1/4 right here, a negative 1. Let's make it a little bit larger so I can fit these numbers in. Okay, well, let's put a negative 1 right here. Okay, so this is from 0 to negative 1 there, right? So in between them is going to be negative 1/2, right? Well, a quarter of the way is going to be negative 1/4. So we do indeed see that negative 1/4 is larger than negative 1/2. Okay, so this is also a true statement. All right, and D, I'm just going to venture to say that D is probably going to be false. Negative 5 is greater than negative 6. Okay, it's actually not false. Every single one of these were true. That's kind of crazy. I just took a stab at that saying that it would be false because, well, I mean, We've all done examples before. We like to, not we like to, but textbooks like to mix in, different solutions, right? But I guess not this one. So -5 is indeed greater than -6 because if we were to look at the number line, I'm pretty sure, let's see, do we have a number line already made for us? Yeah, right here. We see that -5 is here and -6 is here, and we know that -5 is indeed greater than -6. All right, next thing we're going to talk about is absolute value. So in working with the real number line, you may have noticed that any integer and its opposite lie in the same number of units from 0 on the number line. For example, both +7 and -7 are 7 units from 0. Of course, we see that here in the figure, right? Here's 0, +7's over here, -7's over here. In both cases, we are 7 units away from 0. The plus and minus signs indicate direction, and 7 indicates distance. All right. So let's snip this. This is good stuff. So the distance a number is from 0 on a number line is called the absolute value, and it's symbolized by two vertical bars. These two vertical bars you see here. Thus, the absolute value of +7 is equal to 7, and the absolute value of -7 is equal to 7. Similarly, the absolute value of 3 is 3, the absolute value of -4 is 4, the absolute value of -2 is 2, the absolute value of 0 is 0, and the absolute value of -4/3 is 4/3. Okay, so do we see a pattern arise there? Okay, pretty much, yeah, it's whatever the number is, but just the positive component of it, right? So let's just see what this definition says. The absolute value of a real number is its distance from 0 on a number line. Note that the absolute value of a real number is never negative, which makes sense, right? Because the absolute value is basically saying how far away from 0, excuse me, how far away from 0 are you on the number line, right? So it's just a distance. I mean, if somebody says, hey, how far away is Walmart? You're not going to say, oh, it's -5 miles that way, right? You're not going to say that, are you? Right? Because we're talking about a distance. So it's always going to be a positive distance. All right, so starting with example 7. I don't know if we can put example 11 over here. Fill up that space. Okay. Yeah, we'll put example 11 over to the right. All right, so starting with example 7, it reads, simplify each absolute value expression. So all you're really going to do here is just take the absolute value and whatever number's inside it, that's the absolute value. If it's a negative, then just change to a positive. Okay. C is a little bit tricky, but we'll get to that in a second. So the absolute value of 6.3, well, we take away the absolute value symbol, it's 6.3. -5 would take away the negative sign, which is 5. I said C is tricky because, and let's actually kind of work that one out. We have a negative 2.9. Okay, so if we follow along with what we've been doing so far, well, we know that what we're going to do is we're going to take what's inside here and drop the negative sign that's inside the absolute value, but this negative sign comes with it, and that's how we get the absolute value being -2.9. Okay, so example 8. Example 8, we have true or false. The absolute value of -4 is greater than or equal to -4. Okay, so this is going to be true because the absolute value of -4. What's the absolute value of -4? Well, the absolute value of -4 is 4. Okay, and is 4 greater than or equal to 4? Right, it's kind of tricky, but if you think about it, not really, right? Is 4 greater than 4? Well, no, it's not. Is 4 equal to 4? Yes, it is, and that's why it's true. Okay, because that symbol means greater than or equal to. Example 9. if the absolute value of x is equal to 7, what are the possible values for x? Okay, so if we were to have, and of course you can see these answers, and later on in the textbook, well, I will be doing the computation, but these are just one line long, so it's not really a big deal, I think. But anyways, so if the absolute value of x is equal to 7, what does this x have to be equal to? Okay, well, what has an absolute value of 7? Well, the first easy one is 7. Okay, that has the absolute value of 7, but the next one would be a negative 7, right? The absolute value of negative 7 is also 7. And of course, that's what we see here. So example 10, if the absolute value of x is equal to negative 3, what are the possible values for x? Okay, well that's a nice tricky question, right? Because what are the possible values for x if we have the absolute value of negative 3? Well, let's go back to our definition. This last line, note that the absolute value of a real number is never negative. Okay, well if it's never negative, and this is saying it's negative, there's obviously no solution here, right? Because we cannot have an absolute value be a negative number. All right, in example 11, so during the manufacturing of machine parts, certain measurements of the part must stay within a tolerance range or the part will be defective. The quality control manager determines that the maximum amount the length of a screw can vary from its targeted length of 12 millimeters and not be defective as 2 millimeters. So if x represents the maximum acceptable difference in length from the target, either positive or negative, then the absolute value of x is equal to 2. What are the maximum allotment amounts that a screw length can vary from its target? Okay, so it can only vary 2 millimeters, right? So therefore, the maximum amount that the screw length can vary are negative 2 millimeters and 2 millimeters. Pretty easy, right? And if our targeted length is 12, it doesn't ask for it, but if our targeted length is 12, then we can only go to 14 millimeters or 10 millimeters, right? Anyways, that concludes today's lecture on 1.1.